Swayam Prabha. Digital India. Educated India.
And the voltage that is developed across R1 is nothing but this current which we have evaluated here times R1. So, this times R1 is the voltage V1 hat. So, the response by excitation V1 hat by I2 hat equals R1 R3 by R1 plus R2 plus R3, which is exactly the same as in this case. Okay. So, we have exactly the same response by excitation in the two cases as we expected. And finally, let me illustrate it for a case where you have a voltage on one side and a current on the other side. I am also illustrating this. The purpose of illustrating this is also that when you encounter such a situation, you apply reciprocity appropriately. Okay. So, let me take V1 on this side and measure V2 on the right side, and in the other case I will apply a current I2 hat on this side and measure the current I1 hat that flows over there. Okay. Now, in the upper circuit, this V1 appears across the series combination of R2 and R3. We also have R1, but that is directly across the voltage source V1, so it has no effect. So, V2 is simply V1 times the resistance divider ratio, which is R3 by R2 plus R3, or V2 by V1 is simply R3 by R2 plus R3. Okay. And in the other case, what happens? We have a short circuit on this side. So, that means that no current flows through R1. Across that we have a short circuit. So, we just have two resistors R3 and R2 in parallel with the current source. Okay. I hope all of you are able to see that. Otherwise, you can see that the terminals of the current sources are here, and terminals of R2 are exactly the same, and terminals of R3 are also exactly the same. That is, they are connected to the same nodes. Now, the current divides between R3 and R2. The current flowing through R2 in this direction is given by I2 hat times R3 by R3 plus R2. This is from the current division theorem. Now, all of it flows into this short circuit, but this current I1 hat is taken in the opposite direction. So, the actual current I1 hat is minus I2 hat times R3 by R3 plus R2. Okay. Again, if we calculate the response by excitation, I2 hat I1 hat by I2 hat equals minus R3 by R2 plus R3, and you can see that these two ratios of response by excitation are related by a factor -1, exactly as we expected. Okay. Now, it turns out that this reciprocity theorem is very useful in many practical situations, and one such situation is where you have a number of sources in a circuit and you want to calculate the response at a given point, whether it is current or a voltage between 2 points. Okay. Now, instead of calculating the response from multiple sources, what you can do is use reciprocity, interchange the locations of the source and the response, and calculate all these responses to a single source, which is definitely easier. Okay. And by using reciprocity theorem, you can get all of the original responses that you wanted. It turns out this is very useful, and it is used in circuit simulators also, particularly for noise analysis, where you have noises from many parts of the circuit affecting your output. Okay.
You've already seen the proof of reciprocity in resistive networks using Tellegen's theorem. Here what I'll show is an alternative proof using basic circuit analysis. Okay. So what I'll do is I will consider a three terminal 2 port. This is port 1, port 2, and this is the common terminal, and the important thing is that this is resistive. Okay. Now let's say, just for the sake of it, I will drive it with I1 on this side and I2 on that side. Okay. The reason to do this is pretty obvious. I would like to use nodal analysis for the analysis of this. Now we know that nodal analysis is most convenient when you have only resistors and independent current sources. Okay. Now what I'll do is this network itself is quite arbitrary. There can be any number of nodes inside. So I will label this as node N1 and this as node N2, and inside there could be any more number of nodes, and I will call them N3 to N capital N. Okay. So there are a total of capital N nodes in the circuit. Now if you set up the nodal analysis equations for this, N1, N2, a number of rows up to N capital N. And remember, this is a purely resistive network, and the only independent sources in the circuit are I1 and I2. Okay. So now I will have some G matrix. This is the conductance matrix times the variable vector V, which is V1, V2, where this is V1 with respect to the common terminal, and the voltage here is V2, and after that you have V3 all the way to V capital N. Okay. And G times V, the unknown vector, equals the source vector, and the source vector consists only of two non-zero elements, I1 which is being injected into node N1 and I2 which is being injected into node N2, and the rest of it is 0. Okay. Now of course, because the network is purely resistive, this G matrix is symmetric. Okay. So let's say I have G11, G12 all the way to G1n here. Now the first element of the second row, first column and second row will be also G12. Okay. G22, etc., G2n, and similarly here we have G13, G23, and so on. Okay. So this will be symmetric because we don't have any control sources in the circuit. The network is purely resistive. Okay. Now for reciprocity, basically I need to find the relationship between let's say V1 and I2 and V2 and I1. Okay. So what I'll do is I'll try to eliminate all the remaining variables. So for that, let me subdivide this matrix into 4 pieces. Okay. So there are 4 submatrices here, as you can clearly see. You have one and another one and another one here and yet another one there. Okay. So let me write that let me write those things as GA and GB, GC and GD. Okay. Now clearly GA is just a 2 by 2 matrix. GB has 2 rows and n minus 2 columns. It is 2 times n minus 2, and GC is the complement of that, which is n minus 2 rows and 2 columns, and GD has n minus 2 rows and n minus 2 columns. Okay. And this times the variable vector V equals the source vector I. Okay. Now, because the G matrix is symmetric, we can tell a few things about this. First of all, GA will be a symmetric matrix. GD will also be a symmetric matrix. And also, if you look at GB and GC, GC is nothing but GB transpose. Okay. Now, what I will do is, this variable vector V, let me write it as V1, V2, and then the vector of the rest of them, which I will simply call Vx. Okay, this itself is a vector. Vx has n minus 2 elements in it. Okay, and that will be equal to I1, I2, and all zeros here. Okay. Now I will write this as two separate equations. The first part corresponding to these two rows is GA times V1 V2 plus GB, let me denote it like this to make it clear that these are matrices, GB times Vx equals I1 I2, and for this part I have GC times V1 V2 plus GD times Vx equals vector of all zeros. Okay. So what I will do is basically I eliminate Vx from these two equations, that is all. It is just like eliminating a variable from two linear equations, except that we have now vectors and matrices instead of scalar coefficients and scalar variables. Okay. So, but that does not pose any particular complication. Okay. So, if I call this 1 and 2, if I solve for Vx in the second one, it is clear that Vx will be GD inverse times minus GC times V1 V2. Okay. And I will use that in 1. By the way, this means that GD has to be invertible, and we won't go into the complication. We will assume that GD is invertible. Okay. Then what we have is, if we use this in 1, it is pretty straightforward. We will have GA minus GB times GD inverse times GC, this whole thing. Remember, this is a 2 by 2 matrix. V1 V2 equals I1 I2. Okay. Now from this it is pretty clear that this 2 by 2 matrix times V1 V2 equals I1 I2. Okay. So if you think of this as a 2 port, this entire thing is the Y matrix of the 2 port, right, or the inverse of this would be the Z matrix of the 2 port. Okay, because what is the Y matrix after all? Y times V1 V2 equals I1 I2. It is the matrix that relates the port voltages to port currents. Okay. So now let's examine the Y matrix of this. The Y matrix of our two port is GA minus GB, GD inverse, GC. Okay. So first of all, we know that GC is GB transpose. Okay. So this is equal to GA minus GB, GD inverse and GB transpose. So first of all, GA itself is symmetric, that we knew earlier, we discussed that. And if you look at this part, we have GB, GD inverse and GB transpose, and to check for symmetry, obviously you just take the transpose of this. What will you get? If you have three matrices A, B, C transpose, you know that basically this is C transpose times B transpose times A transpose. Okay. So if you transpose this, what you will get is GB transpose transpose, that is corresponding to this one, times GD inverse and transposed, and finally GB transpose. This comes from here. Okay. And clearly this is equal to GB GD inverse transpose. Remember, GD itself was symmetric, therefore GD inverse is symmetric. So GD inverse transpose is the same as GD inverse, and finally GB transpose. So the transpose of the matrix is the same as the matrix itself. So this is also symmetric. This was symmetric. We knew this earlier. And from these two, clearly, if you subtract one symmetric matrix from another, you will get yet another symmetric matrix. Okay. So what this shows is that this Y matrix is symmetric, which means Y21 is Y12. Therefore, our resistive two port is reciprocal. Okay, reciprocity means that Y12 equals Y21. So instead of starting from Tellegen's theorem and getting these results, we could also do it by defining a two port, and we have some two port parameters. We try to calculate the two port parameters from basic circuit analysis, in this case nodal analysis, and you can find that the Y matrix happens to be symmetrical. Of course, if you find any one parameter said to be symmetrical, the rest of them follow the same symmetry. Now the Z matrix will also be symmetrical, and if you look at G or H parameters, G12 will be minus G21 or H12 will be minus H21 and so on. Okay. So this is an alternative proof of reciprocity in resistive two port networks.